Let's talk about one of Java's handiest features, something you probably use every single day, maybe without even thinking about it, autoboxing. I mean, on the surface, it's just this brilliant piece of compiler magic that makes our lives easier. But lurking just beneath that surface, it's hiding some really deep traps that can lead to some tricky bugs and, yeah, even serious performance problems. So why does autoboxing even exist in the first place? Well, it all comes down to solving this fundamental dilemma in Java. On one side, you've got these lightning-fast, super simple primitive types. And on the other, you have these powerful, flexible objects. What do you do when you need the best of both worlds? And that dilemma is there because of how Java was designed from the ground up. You can really think of it as a language with two totally separate worlds. You've got the world of primitives, and you've got the world of objects. And they play by very different rules. For a long time, trying to connect those two worlds was, frankly, a bit of a pain.
Okay, let's really break this down. Primitives, like ant. They're like the raw ingredients in your kitchen. They're fast, they're lightweight, and they live right on the stock, which is a super efficient place in memory. Now, on the other hand, you have objects like integer, which we call wrapper classes. These are more like packaged goods. They're way more flexible, they can be null, which is a big deal. And here's the key. They can be put into things like collections, which, you guessed it, only work with objects.
And this is exactly where the magic comes in. To bridge that gap and just make everything smoother for us developers, Java introduced autoboxing. It's this elegant, almost invisible solution that lets us jump between these two worlds without even breaking a sweat. So at its heart, autoboxing is just the compiler automatically wrapping a primitive int into an integer object for you. And the reverse of that is called unboxing. It's really that simple. Something that used to be a manual chore now just happens silently. You can just write integer boxed equals 10 and it works. Same for int primitive equals boxed. It feels like magic, right? But what's actually going on under the hood? And here's the big reveal. This convenience is what we call syntactic sugar. It just means the code looks cleaner and is easier to write, but the compiler is secretly doing extra work behind your back. It's rewriting your simple code into actual method calls, integer.value for boxing and .intValue for unboxing. And understanding that this isn't magic, it's hidden work, is the absolute key to avoiding the traps we're about to walk into. Okay, let's dive into our first trap. And this one is a classic. It catches even really experienced developers off guard. It's all about how we compare these wrapper objects. All right, take a look at this. I mean, it doesn't get much simpler, does it? We're just creating two integer objects, x and y, and we're giving them the exact same value, 128. They look totally identical. So the natural thing to do next is to compare them. So here's a little pop quiz for you. What do you think happens when we use the double equals operator here? Is this expression going to return true, or is it going to return false? Take a second and think about it. It returns false. And if that just surprised you, trust me, you are not alone. There's a reason this is one of the most famous gotchas in Java interviews. So, why on earth does this happen? Okay, so here's the breakdown. When you use double equals on objects, it's not comparing their values. It's comparing their addresses in memory. It's asking, are these two variables pointing to the exact same object? Now here's the twist. For performance reasons, Java keeps a little cache of integer objects for common values, specifically from -128 to 127. So if our number had been, say, 100, double equals would have been true because both variables would point to the same cached object. But 128 is outside that cache. So Java has to create two brand new, separate objects in memory. The takeaway here is so important. To compare the actual values of wrapper objects, you must always use .equals. Let's move on to our next danger zone. This one's maybe a little less subtle, but it's just as deadly. The dreaded null point exception that can just pop up out of nowhere thanks to unboxing. So here's the setup. Wrapper objects can be null, which can be super useful. We have an integer here called maybe, and we've set it to null. Then we try to assign its value to a primitive int n. Now this code compiles just fine, no errors, no warnings. But what happens when you run it? And boom, null pointer exception. But why? Well, it goes back to that hidden method call we talked about earlier. To get the value for the primitive int, the compiler secretly inserted a call to maybe.intValue. But of course, maybe is null, and you simply can't call a method on a null reference. That's the trap. The lesson is crystal clear. Anytime you're about to unbox a wrapper object, you have to be absolutely sure it's not null first. All right, on to our third and final trap. This one won't crash your program, but it can secretly slow it down to a crawl. I'm talking about the hidden performance cost of autoboxing, especially when it's happening inside a loop.
Take a look at this. It's a super common piece of code, right? We're just adding up numbers from a list of integers. But that line, sum plus I, it looks so innocent, but it's actually a performance bomb. Let's say your sum variable is a primitive long. Well, on every single trip through that loop, the integer I has to be unboxed into a primitive int before it can be added. If your list has 1,000,000 items, well, that's 1,000,000 hidden unboxing operations, creating a ton of extra work and temporary objects for the garbage collector to clean up.
And this graph really just says it all. The performance cost isn't just some theory. It is real, and it is tangible. As you can see, a loop that just sticks to primitive types can be massively faster than one that's constantly unboxing. In those really performance-critical parts of your application, this difference isn't just noticeable. It can be the difference between fast and unusable. So how do we fix it? Well, the solution is to stay in that fast, efficient world of primitives whenever you're doing heavy-duty calculations. Instead of a list of integers, maybe use a simple int array. Or even better, use Java's fantastic primitive streams, like intstream. They are literally designed for this exact problem, and they avoid all that boxing overhead completely. Okay, so we've covered the convenience, and we've walked through the major traps. Now let's pull everything we've learned together into a practical, no-nonsense checklist you can use to write clean, safe, and really efficient Java code. Here it is, your new go-to guide. Number 1, stick with primitives for math and in tight loops where every nanosecond counts. 2, use the wrapper classes when you need things to be nullable, like values from a database, or when you're working with generics and collections. 3, this is the golden rule. Always, always use dot equals to compare the values of wrapper objects. Never equals equals. And 4, before you unbox, just ask yourself, could this thing be null? It'll save you from that nasty null pointer exception. So there you have it. Autoboxing is an incredibly powerful tool, but like any powerful tool, it comes with a few rules. By really understanding what's going on behind the scenes, the caching, those hidden method calls, the performance costs, you can really harness all its convenience without falling into these traps. So the question I'll leave you with is this. Now that you know what to look for, where are these hidden autoboxing issues lurking in your own projects? Thanks for tuning in.